If you're working on software, you need to understand coupling and cohesion. These are fundamental attributes in every system, not just software projects, and their implications are far reaching. The more intentional and aware you can be about using these principles in your system, the better off you'll be. It's better if your design doesn't happen by accident and is instead a strategic choice. I've worked on a lot of software systems, both big and small, and until recently, I haven't had enough awareness of these principles. The words aren't talked about enough, at least not at a deep enough level. And as a result, it's left a lot of things to chance. Things just kind of emerge. Sometimes good, sometimes bad, and I've mostly felt like I'm a victim to them. I've been learning more and more about cohesion and coupling, and it's been revealing. It's like seeing a new light in the color system, a new color in the light spectrum. All of a sudden, you see it everywhere. I now know our system design doesn't have to be an accident. We can be more intentional, and we can design systems to be what we actually want. I'm going to walk you through what I've learned about cohesion and coupling so that you too can start to see the design systems in your life and make better decisions as a result. I'm going to break this up into separate videos because there's a lot to cover. In this video, we'll do an overview of coupling. Another video will look at cohesion. Another video will take a look at coupling and cohesion combined, and we'll probably do a couple in between as well. We'll see how it goes. I'm starting with coupling because I think this is more familiar to people. You hear it tossed around a lot, but I don't often hear it discussed super deeply. You'll hear phrases like, this is too tightly coupled and that is too tightly coupled, but what does that actually mean though? Coupling refers to the amount of interdependence between software modules. Or it could be any system module for that matter. Another way to say this is, will a change in one module affect or require a change in another module? Can this thing be changed by itself? This doesn't have to be software modules either, like I said. It could be the modules or elements or components, whatever you want to call it, of any kind of system. Could be business units, furniture, economies. The possibilities are endless. And like many things, coupling exists on a spectrum. Modules can have low coupling, they can have high coupling, they can be somewhere in between. What this means really is that we don't get rid of coupling. I often hear it talked about pejoratively. Any system will have coupling, as long as there is more than one module, which there really has to be for it to even be called a system. We will be dealing with some form of coupling as long as we're in that place. It's just the name of the game. The more important question is, how will we use this to our advantage? Are we aware of the coupling? What kind of coupling exists and how much? Understanding questions like these can enable us to make coupling work for us rather than against us. Another thing that's generally accepted about coupling is that low coupling is good and high coupling is bad. I'm seeing more and more though that isn't really always the case. Whether you want high or low, it's situational. Like so many things, it depends on context. There are trade-offs with both, and we want to be clear about what those are so we can make informed decisions. To better understand these trade-offs, let's take a look at the world of toys for an example. Let's take a single toy car and compare two different approaches for building it. On the left, we have the Lego way, the quintessential low coupling example. It's very modular and very fun. On the right, we have the die-cast way, the opposite of modular and our high coupling example. Neither of these is wrong or bad, they are just different. And they have different strengths and weaknesses depending on the situation. Let's take a look at how these compare across a few different dimensions. Let's first take a look at flexibility and continuity. The Lego car is super flexible and extensible. It's much easier and less expensive to change things about this. I can change the color of the pieces. I can make it convertible with scissor doors. My imagination is the only limitation. When systems have low coupling, it's much easier to switch pieces in and out. The pieces don't depend so much on one another, so they care less about if one is swapped out for another. The other side of this is the die-cast version, which is rigid. You can't really change much without breaking it at a fundamental level. Each of the connection points expects one and only one other piece to fit there. If you want to change that, you have to break it, melt it down, start over. Highly coupled components know and expect a lot about the components around them. They are designed to work specifically with the other components in mind, and so they're not open to using others. What the die-car loses in flexibility, it gains in continuity. The die-cast car looks much nicer. Literally, it's seamless. It's crisper and more realistic than its Lego counterpart. It's smooth and shiny. The whole thing flows together for a nice, aesthetically pleasing experience. This is an upside of highly coupled components. They know about each other, and so they deliberately guide you from one piece to the next. The low coupling Lego example, on the other hand, is very disjointed. You might have a hard time telling which specific type of car this is. You can see all the imperfections, gaps, and the places where it doesn't fit together so well. It's just not as visually pleasing. And this can be a big drawback with low levels of coupling. It makes for lower fidelity experiences. A principle that can help you remember the trade-offs between flexibility and continuity is snap for change, glue for constancy. The amount of coupling you use very much depends on how much you want or expect the system to change. If your system is changing all the time and it's evolving all the time, like most software projects I've worked on, then low coupling pieces help you a lot. If you don't want the pieces to change, or the people you're serving don't want them to change, or you're just working on a type of project where things don't change very much, then high coupling is a great choice. The people who made that die-cast car, they never intended anyone to change it. It was expected that it would be taken as is, and that the consumers of that product would prefer to stay the way it is. Make sure the amount of coupling you're using makes sense for the amount of change that's occurring. Next up, we'll examine durability and resiliency. The die-cast model really shines in the realm of durability. My kids can drop this thing thousands of times on concrete, hardwood, you name it, and it won't get more than some scratches. It's tough. This is often something highly coupled designs are going for. They are trying to not break in the first place. They try and control the quality tightly, eliminating flaws. Sometimes this is a style preference, sometimes it's the only option. If you're building airplanes or surgical equipment, failure isn't an option. Lego sets, on the other hand, will definitely fall apart if my kids drop them. I have a bunch of sets in my office, and my worst nightmare is that my kids will knock one off the shelf and send pieces flying everywhere. Or worse, pull the whole thing down. I'm scared of this because I know stuff is going to break. This can be a downside of low coupling. The pieces are modular, and so they don't have strong connections with the other pieces around it. The more connection points, the more failure points. While low coupling adds more potential for breakage, it makes up for it in another way, which is resiliency. When it breaks, it can recover from that breakage relatively easily. It might take some time, but you can restore the set back to its original form without buying any new parts or doing anything overly difficult. One of the promises of low coupling systems is this resiliency. There's potential even for self-healing. By keeping the pieces independent from one another, the failures have the potential to stay isolated. You can break one part without breaking all the other parts. You can even fix just that part without getting involved with all the others. High coupling systems tend to not be so resilient. They may not break as often, but when they do, it can be more devastating. It's more brittle. Take our die-cast car, for example. If a piece of that breaks, I wouldn't be able to put it back together like I could with the Lego version. At best, I'd have to try and reorder spare parts, if they even make them, and try and find specialized tools or materials to put it back together. I'd be lucky if it's even the same when I'm done. I might not be able to even get it back to original form, and instead would be left with some permanent scars. Because highly coupled pieces are so tightly connected, bringing down one piece can bring down many other pieces, or even the whole system. The way I like to remember this is that strong coupling survives hits, loose coupling survives change. remember that the kind of coupling you're using has an influence over the durability or resilience of your system. If it's more important to you to avoid any kind of failure up front, and you're in an environment where low amounts of change is acceptable, then you're going to be leaning towards higher coupling. On the other hand, if there's going to be lots of change happening, then you'll need to be prioritizing resilience or bouncing back from failures, which will mean lower coupling. Doing both is sometimes possible, but it's very expensive. Next up, we'll examine isolation and optimization. I mentioned how with low coupling you can isolate failures. Well, this is also true of changes. If you need to change something about the system, you could change it in one place without changing everything else. This is part of why this design choice gives so much flexibility, like we mentioned earlier. You can make small, inexpensive, manageable changes without appending the whole thing. On my Lego car, I could change the style of the doors, the style of the fender, or spoiler without having to change anything else. This isn't the case with the highly coupled die-cast car. Trying to make a change is more expensive because it cascades to all the pieces around that change site, not just the part I wanted to change. If I wanted to add scissor doors, I'm going to have to take the whole side of the car apart, and then I'll have to take the front of the car off, which means I'll take the lights off, and I'll be lucky if it stops there. And I might not even be able to get it back together. At this point, I might as well have bought a completely different car. This is something to be aware of when you're choosing a highly coupled system. Changeability is easier for lower coupled systems and harder for higher coupled ones. It's the inverse for optimization. It's easier for highly coupled pieces. You can make decisions in each piece that will make it work faster, nicer, stronger with the pieces next to it. This can be really important and sometimes essential in different parts of the system. A common place I've seen this is in web applications between a front-end UI and a back-end server. Many applications have a separate code base for their UI and a separate code base for their backend, and it's often the case that this backend only exists to serve that front end, and that front end only exists to work with that very specific backend. They know a lot about what's going on with each other. The same team is probably working on both. This allows the backend to be optimized for that front end. It can adjust how it operates with certain views in mind to make them faster. This isn't as possible when there's low coupling. When components know very little about one another, they can't optimize across the boundaries. They'll be serving a broader range of use cases, usually unknown use cases, making it harder to optimize. This means there's going to be inefficiencies, parts that slow down or weaken the overall system because they don't work as well with the other pieces. This is like our Lego car. Any Lego piece could connect with any other Lego piece. It can't optimize for any one set. It can't optimize to be a car because it might also have to be a building or a spaceship. To make matters worse, the low coupling also introduces overhead inefficiencies. Each connection point requires communication overhead. There's a cost to going through each of the gaps. You see this in software with service-oriented architectures where between each service you need to do all these things. You need to serialize and deserialize the data, send it over a network, do some translation when formats are different. The more gaps you have, the more potential slow spots you have. One more thing to consider when you're deciding if you want to go with low coupling. A way to sum up the optimization and changeability trade-offs is lock in for speed and loosen to adapt. When you run into situations where something needs to go faster, you might need to look at tighter coupling between components. If you're in an environment with a lot of change, you want to keep things loose so that those changes are easier. But in those places where speed is more important, it's okay to tie those things together. There's other things you may need to optimize for as well besides speed, such as appearance, memory, energy, simplicity, consistency, or certain functionality that can be okay so long as you're weighing the cost of it. Last on our list is scalability and cost. A very popular reason for going with low coupling is about scalability. It tends to be cheaper to scale systems that have low coupling. Take a look at the Lego car, for example. If you want to make that car bigger, life size even, you just add more bricks. Each brick is relatively cheap to make, and you already have the setup to create them, so you just do more of it, and you get a much bigger system from it. This is the same strategy lots of software systems use with service architectures and horizontal scaling. You have distinct low coupled services, and when you want to support a bunch more traffic, you just add more servers running the same software. Now contrast this with our die-cast car example. It's not going to be cheap to scale that to be a life-sized model car. You're going to have to get brand new machines, bigger machines to manufacture these new parts from scratch. You'll have to design and reconstruct brand new pieces and put them all together. It's harder to scale a system that is tightly coupled. Pieces tend to expect that the other pieces around it will be a certain size and shape, and so you hit limits with being able to just add more pieces or stretch a piece of that size. They can only stretch so far. However, it's often cheaper up front to do the tightly coupled version. You can usually get something out the door faster because you only have a very specific set of functionality in mind. You also don't have all these complexities and overhead of trying to figure out all these complicated interfaces and boundaries of disparate components that takes long and can slow the initial design and release down. You can see this in the actual retail price of our toy car examples. The die-cast highly coupled model only costs around $8. Compare that to our Lego car example, which costs around $60. They look like they're trying to do the same thing. There's a big price difference. And some of that, of course, is name branding, so it's not complete apples to apples comparison, but I think the stark price difference makes the point that low coupled designs can be more expensive at a small scale than a high coupled design. A helpful phrase to remember the scalability and cost differences: tangle to test, separate to scale. It's better to use high coupling if you don't know something's going to scale. If there's uncertainty about the capability of what you're going to do, then you should stick with high coupling until you're more certain. You could also say that you should stick with high coupling when you are experimenting with solutions until you know that they solve a problem. Here's the catch though. Once you have more certainty that you're going to swing for scaling your solution or system, you need to make a big investment in low coupling and distributed computing so you can get that capability. And this is where a lot of systems can fall short, because once they discover that their high coupled solution is working, they get excited and they get investment money and they have all these deadlines and they rush to scale, and they don't stop to re-architect and separate those components, at which point the scaling becomes slower and more expensive. Now, we've covered a lot of different attributes of low and high coupled system. There's a lot here, and the answers aren't simple. There's a lot of situational context that drives when to use which and where, and there's also stuff in between. I haven't even covered yet the different types of coupling there are and how that can factor in. We'll save that for another video, but for now, let's review some of the main takeaways from this so that we can use them in our systems. The first thing we looked at was how we can snap for change and glue for constancy. This was talking about flexibility and continuity and the trade-offs between those. After that, we took a look at how strong coupling survives hits while loose coupling survives change. This one is all about reliability and durability, and how loose coupling can be more for reliability, while strong coupling tends to do better with durability. We then took a look at scalability and cost, and we remember this one, not scalability and cost, optimization and isolation, and we remember this one with lock in for speed and loosen up to adapt. Now we're getting to scalability and cost, which is on our mnemonic for this is tangle to test and separate to scale. And the last thing I'll add, which we haven't really gone over too much, is that it's not better, high coupling is not better or worse, they're just different. Low and high coupling are just different. That's the main takeaway from all this, is that we should be understanding the decision we're making and trying to understand the cost. Coupling is a tool and an attribute of the systems we create. If we can understand more about that, we can be more intentional in using that to our advantage. We can make it work for us rather than against us. It's a big topic and there's a lot more to cover. So please do subscribe so that you can catch the next videos about this and more. Also, share some examples in the comments of systems you've seen and the levels of coupling they used and what the effects were. We're all part of systems, they're all around us. And I'd love to hear more real life examples from your day to day and what you've seen and how these principles apply. Thanks so much for watching. We'll see you next time.